this video, we're going to discuss the organization of a computer system, specifically with regard to input and output devices. So to start off with, this is a graphic of what a computer system might end up looking like. We have the CPU and several input-output controllers, like your disk controller, the USB controller, and the graphics adapter, which all need to connect to memory in order to exchange data. We can refer to all of the input-output devices that need to communicate with memory because they are doing so on behalf of an input or an output device as device controllers. So these connect through a common bus, and typically only one of these devices can be communicating with memory at a time. Since only one of these can be communicating with memory at a time, we would refer to the interleaving of accesses between the CPU and devices that are competing for memory cycles as concurrent accesses. In terms of the operation of the computer system, each device controller is in charge of a particular type of device and has a local buffer in which it can store a select number of objects. The CPU is in charge of moving data from or to main memory to or from those local buffers. And the input and output is from the device to the local buffer of the controller. The device controller is going to inform the CPU that's finished its operation by causing an interrupt. So interrupts are important because they are part of what really drives an operating system's use. But first, it's important to understand what they are. When we have an interrupt occur, typically that is because we have an input or an output device that needs to have its data handled by having that data transferred from memory to the device controller or from the device controller to memory. So an interrupt is going to transfer control of the interrupt service routine, generally through an interrupt vector. So the interrupt vector is what the CPU sees, and it contains the addresses of all of the service routines. It's the interrupt architecture's responsibility to save the address of the interrupted instruction. So this part has to happen in hardware for anything else to make sense. Only one interrupt can be occurring at a time. In order to enact that, all incoming interrupts are disabled while another interrupt is being processed, so that there are no lost interrupts. If it comes from a I/O device, input-output device, controller, typically refer to this as an interrupt. But if some process that is running on the CPU happens to cause an error or extend a service call, a trap is issued instead. The trap is also responsible for saving the address of the interrupted instruction. So a trap is a form of interrupt. The operating system is going to preserve the current state of the central processing unit by storing the registers and the program counter. The interrupt vector helps determine what type of interrupt has occurred. So this can be done either through that interrupt vector, or it's possible to poll all of the I/O devices and the CPU to determine what kind of interrupt was enacted. The operating system contains a different set of code for each different kind of action that should be taken for each different type of interrupt. So here's an example of what an interrupt timeline might look like. The top line is oscillating between the user process executing and some I/O interrupt processing. The I/O device is oscillating between being idle and transferring data. So the CPU can have a user process that is executing at the same time as the I/O device is transferring data from memory to the I/O device itself, or from the I/O device's local buffer to memory. Top line shows oscillation between the user process executing and the I/O interrupt processing. So the I/O device is able to do transfer from the I/O device to the buffer controlled by the device controller. But when that transfer is done, an interrupt is triggered, which will result in the user process being kicked off the CPU and the I/O interrupt being processed. So we see this happening twice on this chart.